So the title of talk is India's contributions to exploratory lunar science. And this is going to be very, very light in content, but very interesting. And if you just ask me to summarize the whole talk, I would just, flash this particular image. Why? Because this is showing our journey to moon exploration, starting from orbiter, then attempt of landing, and then a successful landing and rover exploration through rover. So this is the image of our lander, Vikram lander, taken by our rover Pragyan. And what it shows is this ramp from where this Pragyan came down, and then a lot of experiments on lander. So this one is Chaste. Here you can see this seismometer and some cameras and all. From this particular picture itself, there's a lot of things, very interesting facts, what you can learn about moon. For example, the terrain, the type of terrain, the kind of differences in the morphology or the surface structure, you can say, and that gives us perspective. So we would not get this kind of understanding if we would have not started with exploration. So that is the importance of exploration. And obviously moon is the nearest to us, so moon serves as a natural laboratory for us because it's a bit easier to reach there compared to Mars or to Venus, which are also equally interesting objects. But moon is kind of natural laboratory where you can go, you can experiment, and you can learn for further exploring our solar system. So let's start with moon, because obviously I don't have to just conclude in one slide. So I go ahead with this. So if you have seen moon, and if not, today is the best time because today is full moon, and you should obviously look outside tonight, and you should start observing by your own, because your eyes are also doing remote sensing. So basically, if you look to moon, you are familiar with this side of the moon. But this side of the moon was unknown to us till the first spacecraft, Luna 3, provided us the images of the far side of the moon. And the interesting fact is that both these sides look quite different. Until we did not have this image of the moon far side, our understanding was that the far side or the back side of the moon should also look very similar to its near side, or to the side which is facing to Earth. Because there is no, why we should expect these kind of differences? And it is puzzling that we do see this kind of differences. So the first time when scientists started getting these images, we were wondering, is it the correct image we are looking on? So this is quite interesting about moon, and though it is so near to us, but there are still many unknowns. But along with unknowns, because we have a systematic program of exploration, and we started in 2008, but before that, from NASA and from USSR, we had series of missions, and those missions also, and also the telescopic observations, provided us wealth of data and a basic understanding. So based on that basic understanding, we know that the moon spins on its axis and rotates almost at the same time, once in every 27 days. And that is the reason why you only see one side of the moon, not the other side of the moon. Okay. So this synchronization means you must have heard that Chandrayaan 3 mission was planned for 1 lunar day, and that 1 lunar day means 14 Earth day. So that means that at any particular time, if you are on moon, you will be having 14 consecutive days of sunlight and 14 consecutive days of night. Okay. And then another interesting fact is, we know now that moon is drifting away from Earth. So does it mean that moon was very nearby to us in the very initial phase of the evolution of Earth Moon system? This is again a very interesting question. And because we have, even Chandrayaan 3 had a seismometer on board, and then other missions, also Apollo missions, had a seismometer, and we know that moon also has quakes. Though moon is one plate planet, but it also has shaking. So the concept what we had initially, that moon is kind of, nothing is going on the moon, is not true. Now we know with our exploration plans that that is not the correct statement. So moon is also shaking. Moon is also basically, lot of things are going on the moon, which we need to understand. Another very interesting fact about moon is water on the moon. All of you must have heard about it, but no liquid water. Okay, so it is not in form of liquid water because there is a perfect vacuum on moon. So you cannot have liquid water on the surface, but you can have water in the form of ice and mixed with soil or regolith. And this understanding is also very recent, because initially our understanding was that most likely moon is bone dry. So there is no water, but the new series of experiments, exploration provided us detail that no, that is not the case. We have to revive our understanding, and we have to, come up with next set of questions, that there is water on the moon, and if that is the case, how we can utilize it. Because if we are planning for base on the moon, or if you want to have resources from the moon, water is something which you would like to extract and use. Another important fact is that initially it was thought that moon is a airless planetary body, and that is still we are continuing with that thinking, but we have enhanced on that in terms of understanding that it do have a very thin and weak atmosphere. Okay, and in this particular direction also Chandrayaan missions have contributed significantly. And then the surface of the moon is fully covered by a very fine layer of dust, or in scientific term we say regolith. It's very similar to what you see in case of Earth soil. And the main surface alteration process, for example, on Earth is rain, wind, and so on. But here in case of moon is space weathering. And if you understand space weathering on moon, basically this information or this knowledge you can extrapolate to understand any airless planetary body like asteroids. And then we have a very good understanding on, but not yet fully understood, is the fact that moon must have formed from a giant impact. So a body might have impacted on Earth, a very huge, like Mars sized body, and that might have actually formed our moon. So there are obviously a wealth of information, and this new data set, new information has opened up new questions. One more interesting fact is that if you look from here, the face of moon would look something like this. Okay. But if you are somewhere in the other part of the Earth, you might see this particular crater, what you can see here on top. Okay, so for example, if you are in a new place, and well, now these are not the conditions because you are very much aware with internet and all, but if that happens, that you want to make yourself familiar with orientation, how would you do? Actually, moon is something which is visible from everywhere, right? So, but if you look from, other side of the world, you may find that the face looks still the same. So the moon is still showing the same face of the same face near side of the moon, but the orientation is upside down. So this is from, let's say, from India, but maybe when you move to other side, and you may see it upside down. So here there's a case. So this is from northern hemisphere, and this is how you would look full moon from southern hemisphere. And what would be the case if you look from equatorial area, exactly, equatorial of the of Earth? That is a question which you should be coming up with the answer. So why at all we should be exploring? So one question is that now we have our systematic exploration path, but why should we explore at all? So here I would like to quote Bill Andrews from Apollo 8 mission, and I would just read this because it's very beautiful quotation, what he summarized very nicely. We came all this way to explore the moon, and the most important thing is that we discovered the Earth. So whatever exploration is there, it's actually related to our own world, because we want to protect, we want to understand our world. And we are curious to know for other habitats. So we would definitely like to extend it for searching for other habitats. And planetary exploration helps to develop new technologies, and that further can be, used for economic prosperity. Obviously, we are curious all the time, and we would like to know answers of unknown questions. And with this kind of missions or exploration plans, we team up with international people, and that enhances international cooperation, trust, exchange of culture, and lot of other things which we learn by sharing with each other. So this is why it is important to explore moon. And then, as I discussed already in previous slide, we are curious. So now I'm moving from, I'm trying to take you towards scientific, objectives of exploration. So in case, particularly in case of moon, I have listed down these 5 top questions which comes in my mind. Obviously, there can be plenty of other questions, but if I have to categorize, I would say that we still have to understand about origin and evolution of the moon, because when we talk about moon, it is basically the Earth-Moon system. So because moon is affecting Earth, and you know that we are getting these tides on Earth, and basically could be that we are having habitability, or we are having life on Earth because of this tidal effect, which is like, heavily mixing, churning, and providing, exchange of energy. So in that case also, moon is a very important object to understand, because when we talk about moon, it is basically the Earth-Moon system which we are trying to understand. So origin and evolution of the moon, and if I further divide it, I would say that we would like to know how did the moon form. We have some idea that this is most likely due to giant impact hypothesis. So basically a Mars size object hit Earth, and there's mixing of this, and this particular such a huge event uh, generate a disk of debris, and that eventually at a certain distance start forming the moon. But there are many uncertainties here, and there are several models which tells that could be that moon is made of mainly the mantle of earth, or maybe the maximum contribution from Theia, and because we have some kind of similarities between earth and moon, but there are certain dissimilarities also which we need to still understand. So this is something which we still have to find out. Then we also have to understand that is it that early earth, uh, I mean basically what kind of information we can get from moon about early earth, because earth is an active planet. So here we do not have all those evidences. But once moon is found, and because moon is not very active, that's why whatever information is stored there, it will be staying there as it is until unless you disturb it. So that's why moon is like a kind of place where you can try to get the evidences, the old evidences. And is there, like, when this kind of kartik formation happens, would there be a fully molten magma from where the crystallization starts, or would it be a partial melting? Because that has implication towards understanding its evolution and its geology. So these are again, part of questions which we need to understand from origin and evolution of the Earth Moon system, I would say. Then lunar volatiles. So obviously, when we talk about volatiles, the first thing comes in mind is water. But water is not the only volatile we are looking for. There are several other volatiles which are very interesting to explore. For example, there is sodium, which is like, you can basically, now we have from Chandrayaan 2 mission, we have sodium maps for and it at the global scale and so on. So there are several other volatiles which are very important to understand, and uh, these volatiles are mainly important from understanding the accessibility of these resources. So how accessible are they? What is the origin of these volatiles? So if you think that there would be, like, too much of heat during this kind of formation chaotic situation, would there be volatiles still remained in the very initial time? So is it like contribution at a later stage, or is it from the time of the formation? So origin is also not yet fully understood. The distribution is not yet fully understood. And how can we map it? So that is also something which those Chandrayaan missions have significantly contributed in that direction, but there is a lot which we still have to understand. Then permanently shadowed regions, you must have heard this particular term. These are the areas which are always in shadow because of because moon is almost, there is no tilt on its axis. So because of that geometry, there are several areas which are always in dark, like this particular example. So when you have this kind of area sitting in shadow for billions of years, there's a high possibility that you may accumulate volatiles there. So that's why permanently shadowed regions are very important to explore. And this is a reflectance image of this particular crater, Shackleton crater from the southern lunar pole, which shows that what kind of morphology do you expect in this kind of permanently shadowed region. So do you expect ice there or not? The results indicate that yes, but then there are several results. For example, even this one, where we do not see any difference in morphology, which can tell you that there is water ice present. So it is still a very much open question, which we have to understand. Then, if there are volatiles, what kind of transportation mechanism, or what kind of accumulation? How do you get it, and how do you basically release it? So we have some idea from modeling and from observations, like we know that the solar wind from sun is basically contributing towards getting this, superficial water ice that eventually, if it goes and reside in these kind of places, it stays there undisturbed. But then there are several hypothetical elements in this particular graph which we still have to understand. So basically the overall cycle, though we have a good understanding now, but still there is a lot which we have to understand. Then lunar interior. We have some idea from samples because we basically extrapolate it towards the interior, but there are still many open questions. For example, what is exactly the composition of mantle? What is basically the boundary for mantle and crust? And is there molten core in case of moon or not? So there are several questions in that direction. Geological history of the moon. So for example, as shown here, initially might be that there were impacts like this, and then you got some kind of volcanism on the moon, and after this volcanism again some kind of impacting. So this kind of modification processes are there, which are in a chronological order, very important to understand the overall geological history of the moon. And when we say moon, obviously we are also trying to understand Earth-Moon system in an integrated way or in general way. So in a very, very broad terms, moon exploration is very interesting because moon is, you must have seen that now the interest is again revived and everybody is behind moon because, moon, initially we thought that, okay, we have learned a lot about moon, but then a new set of questions indicated that there's still a lot which we can do and we should be doing because again, because this is a nearby object for us. So there is a lot right now going on in terms of we might use moon for mining resources, for example, helium-3, which can be used for getting the nuclear energy sources and so on. We can use moon as base for further exploration. If we use moon as base, obviously what we need is to use moon's resources for fueling, and then we should have a permanent settlement on moon, because if we want to further move out in solar system, moon is the first challenge. So if we can have a permanent settlement on moon, we can think about going beyond moon. And also orbiting space base, and then space tourism. These are the new interesting branches now coming up with a lot of excitement. So here in this particular slide, I want to summarize that moon exploration. For example, here what you see is at the near side, these are the landing sites listed here. And Chandrayaan-3 has landed in the very much southern latitudes, southern highland latitudes. And these are the upcoming moon missions from governmental organizations and private organizations. And as you can see that we also have 2 missions planned, Chandrayaan-4 and LUPEX Chandrayaan-5. The main long-term goal for all these exploration plans are basically to have a permanent base on the moon. This can be, an international effort also, and in order to have these natural sources, water and oxygen, precious metals, rocks, and rare earth elements, and helium-3. So these are mainly the, the long-term plans. And as I also already said, that the moon poles are also very interesting. For example, here the south pole of the moon is shown, where there are several, the shadowed or the dark regions are the permanently shadowed regions, which could be obvious shield for us, and these are the areas where you can have the highest probability of having water ice, and that can be used as a resource. Now coming to our own systematic plan, or our own contribution, we have total 3 missions so far, and 2 more are planned, as I already said. And we started with Chandrayaan 1 in 2008, obviously planning and the overall framing the mission and all started much before than 2008, maybe in 1990 and so on. And the first mission was a truly international collaboration, where we had several instruments from India, whereas a few, for example, the SKICS and SARA in collaboration, and then a few like SIR2, MCube, and MINISAR from outside India. So this was a truly international mission with the total 11 payloads. So you can see that actually, if you look to the name of these payloads, you will understand more or less the objective of these instruments or payloads. For example, terrain mapping camera to have very high resolution images and to prepare a terrain map of the moon, then hyperspectral imager for looking, at a very high resolution, the surface of the moon, the surface composition, the mineralogy of the moon, and so on. Also, this KICS, or this Chandrayaan-1 X-ray spectrometer, working in X-ray regime for compositional understanding, elemental understanding, and so on. So a very nice package of instrumentation. So why do we go with so many of instruments at one go, and why you always look for different wavelength ranges? So this is again a question which should be asked and which should be understood, because you will see the same pattern in Chandrayaan 2 also. So here also we have a high resolution camera. This one was specifically for looking from the oblique views, and mainly for mapping the landing site. Then we had the advanced version of terrain mapping camera, advanced version of KICS here, and this IIRS advanced version of MCube, and so on. So we are always doing multi-wavelength measurements. So basically what we are trying to do is we want to look to moon in different wavelengths. Why? Why it is so? So that is again a question which you should be thinking about. And then Chandrayaan 3 in 2023, where we had a set of instruments on lander, this seismic activity instrument ILSA, and then Rambha, Chaste, and then we had 2 experiments on rover, APXS and LIPS for elemental and mineral mapping, and then we had this shape on the propulsion module to understand the the signature of a habitable planet. So looking to Earth from the moon orbit, considering that if you are looking to an exoplanet, what kind of signature you should be expecting. So here is the answer to the question I just asked in the previous slide, that when you look moon in different wavelengths, you get different information. Okay, so starting from here, from the longer wavelengths, basically, starting from radio and going to NIR, and then to visible, UV, X-ray, gamma, what you see is that you are getting different kind of information for every region of the wavelength. So when you integrate this information, you get the overall information or in-depth information of a specific site or a specific body. And that is the reason that we always go with multi-instrument, looking at different, some are looking to maybe atmospheric composition, some are looking to surface, some have the capability of understanding the inner structure of a planetary body, and so on. So these are the instruments very meticulously designed and selected, and you have lectures on these aspects, so I'm not covering that in very much detail. So now I'm basically focusing on the scientific part. So what is the contribution of Chandrayaan missions to new views of the moon? So there's a significant contribution, and I want to start with the one specific case of technological innovation. Okay, so obviously we are more interested towards science, but science and technology go hands in hand. So basically, we are improving in both the sides with every subsequent mission. So every subsequent mission, we are developing new technology because we are given new challenges. So new technology, new understanding, and based on that new understanding, new scientific questions. So here is an example from Chandrayaan 3. If you look, that it had basically I would say that this is a technological innovation where we had multiple backups for Chandrayaan 3 successful landing, and it was fully automatic landing. We did hop experiment, and that demonstrated ability to take off from a celestial object and land again. Another technological innovation was bringing back the propulsion module of Chandrayaan 3 from lunar orbit into Earth orbit. This was also successfully done, and testing technology for future interplanetary missions, because we wanted to use this opportunity for upcoming missions. And these experiments have taught us a lot, and the data what we have collected is basically a base for further improvement and for innovation. So here is the image. This one is again, both of them are from lander camera, and what you can see is the difference. So these two craters, if you focus in this particular image, you see them shifted, and this is a reference. So this particular reference is there in both the images. So what you see is this is, and these are the rover tracks. And what you see is that this image is before hopping, and this one is after hopping. And with these images, we confirm that this hopping experiment was done successfully. So where are we now? So we, for summarizing this, we had a first successful landing in 1966. We had a human landing in 1969. We have now return samples from Apollo and Chang missions, and then we have a first successful Indian landing at the high latitude region. So this is again first, which is credit to us. Now coming to a few scientific results, and I will be going a bit fast now because I have just 10 minutes left in my hand. So basically, the most important result from Chandrayaan 1 mission, and that is followed by Chandrayaan 2, is confirmation of water on the moon, discovery of water on the moon. So there were indications from previous missions, but this was the first time from Chandrayaan 1 where we saw that as you are moving towards pole, you have this, this is from the hyperspectral imager, and that indicate the presence of water. And this was also confirmed by looking to MINISAR experiment again on board Chandrayaan 1, where we looked to the CPR ratio, the circular polarization ratio, which is a parameter to look for the water ice presence, and there were a few anomalous craters which showed enhanced CPR signature, and that basically indicate that there is a high possibility of having water ice on the lunar poles. Another direct evidence came from our own experiment, Moon Impact Probe, which had a instrument chase on board, and that provided the altitudinal variation. So for example, here hydrogen, this is argon. And what you can see is that as you are moving towards pole, the density increases. So that again indicates the uh, presence of water in form of ice, and these observations were also correlated to M cube or to the hyperspectral data, and it was found in good match. Uh, from Minisar, we have PSR regions which you cannot simply photograph. Those are the regions which you can look from the radar imaging. And this is such one case where you can see that, there is a decomposition of the scattering parameters, volume scattering and backscattering and so on, where you can see that, different colors basically tells you a different kind of scattering phenomena, and that indicate you the soil properties. And here this is the CPR map, and this red areas basically indicate a possibility of having water ice. So from this particular instrument, we could have the catalog of several such craters which could not be examined by the optical cameras. And this more than 95% of polar region was basically mapped in a systematic manner. We also have supportive evidences. So here, for example, a study where not only enhancement in the signature is reported, but also the variability based on diurnal variability is also shown, where in morning you have more water which evaporates, and then by evening you start getting that back. And these are the polar areas where again map is prepared using by integrating data from different sources, which shows you basically the potential sites where you may look for water ice exposures based on these kind of signatures. A new rock type was also discovered using Chandrayaan-1 moon mineralogy mapper spectrometer, and this was quite surprising because this was not actually found from the Apollo samples, and this was basically first reported from this particular area of the moon, and later on there were systematic studies which also reported this kind of lithology from other different areas, and that this particular mineral, pink spinel or the Mg spinel, basically is the one which gets crystallized at the early stage of crystallization, and because of that exposure, one can try to understand the early history of the moon, and this has basically implication for understanding the evolution of the moon. And how do we get these kind of information is by looking to this kind of spectral signature from this reflectance versus wavelength graphs. Another very interesting study or discovery class result is from, again from Chandrayaan mission, is this young volcanism and extended volcanism. So initially it was thought that volcanism stopped something like 3 billion years ago, but the new information, high spatial and spectral mapping, shows that that is not the case, and you may actually get this kind of features which explain that moon is basically active of something so young as something like 50 million years. So a lot of systematic study has been carried out using Chandrayaan datasets. Another catalog prepared for domes. So these are again volcanic features, and for looking to them, you have to look to its morphology, and for that, what you need is the elevation map. So this kind of slope map or this kind of 3D maps are prepared to understand the parameters of domes, and several of these domes are basically reported using Chandrayaan data, and a catalog is prepared. The spectral classification is used for looking to the elemental composition, or a very detailed spectral classifications carried out using again Chandrayaan data. And high resolution maps are prepared now, where we have information of distribution of iron, calcium, magnesium, and a few other elements, which basically tells us about the surface mineralogy and the surface composition, that again can help us to understand the interior of the moon and how this might have evolved. The lunar environment initially was thought very simple, but now after Chandrayaan mission, we know that it is very complex, and a lot of dynamics going on from the day side, night side, and interaction between day and night side. Another very interesting result came out from Chandrayaan mission is the discovery of mini magnetosphere, the strength of the mini magnetosphere. And if you have this kind of mini magnetosphere, because moon do not have the full magnetic structure like earth have, so why do you have this remnant magnetic fields, and how why do you have it, and what is the origin, and basically what is the relation with the surface features. So these are again something very interesting findings out of Chandrayaan mission. Now specifically looking to Chandrayaan 2, which had orbiter, lander, and rover. This is, I will very quickly go through it, because I think, yes, I had just have 5 more minutes. So this was the picture we had before Chandrayaan 2, where a very sparse coverage in X-ray, which basically is a direct way of getting elemental composition. But because of the limitation of this technique, we had a very limited coverage from X-ray spectrometers, but Chandrayaan 2 provided us the first global coverage, and this particular coverage is now substantially revised, and we have even better coverage now from Chandrayaan 2. Global elemental maps are prepared: magnesium, silicon, aluminium, iron, and also sodium maps are available. So this kind of new information have been retrieved from Chandrayaan 2 mission. This kind of detailed landing site studies have been carried out using Chandrayaan data set, Chandrayaan 1 and Chandrayaan 2. So here you can see the alternate and primary landing site of Chandrayaan 3, and what kind of composition and mineralogy you expect, or what kind of thermal behavior you may expect. So these kind of detailed analysis are required before you send your, before you land. So these are also, carried out using the inputs from our previous missions. So I will just skip this particular thing. And then IIRS, basically from Chandrayaan 2, has provided information on OH H2O mapping. So 2 specific studies have been carried out for which tells you spectral unmixing of this, basically telling you the type of minerals you have, and then the complete characterization of this hydration feature in and around the Shiv Shakti point. And this kind of data sets are very complicated, so you need to spend some time to understand these kind of data set, and basically to reduce them in order to get the information, extract the information. I will not go in detail to these things, because I already explained from Chandrayaan 1 point of view. Now with Chandrayaan 2, we have dual frequency SAR, which gives you even further information, because it it gives you all the parameters which help you to basically bifurcate the information and prepare precise CPR maps and basically the decomposition matrix that can be related to a specific kind of scattering phenomena. So this kind of detailed maps are prepared. Now coming to Chandrayaan-3, next level of complicated mission, and this was basically the one lunar day measurement, and it provided us a very wealth of information from because this in situ measurement, you can say. We have now a good understanding on the thermal profile of first a few centimeters, and this ILSA basically help us to understand that.
Ma'am, you have 2 minutes left.
Okay, fine. So some movements which are like related to known activity and unknown activities and so on. So very like very impressive landscape. I will just skip this. Another very important result is from APXS on board Chandrayaan-3, which basically provided us a systematic mapping of 100 meters, and it provided us the information that overall the composition is not changing within 100 meters of the track traveled by the rover, and this is a typical spectrum shown here, and the chemical composition found out of this. So presence of several major and minor elements, and now this particular instrument information can be used as a ground truth for other missions. So I will simply skip this, and now basically now what is the direction? So basically we have some understanding on sources of this volatiles, and how do we basically remove this volatiles. So basically sources and sink processes, but to further understand it in detail, you need landing missions, or you need to go to the extreme south, and in that particular direction now the Chandrayaan-5 LUPEX mission is planned, where we did a systematic study and look for the landing site where we can basically land, and we can get maximum information about these kind of volatile cycle. So I will just leave you with this particular image, where this shows the initial time of exploration. So this is the near side, far side of the moon, the first far side image, and the recent image, and you can see the difference. Though this is also equally important, but you can see the finer scales detail what we can now get with the much better instrumentation and much better understanding what we have developed from 1960s to now. Thank you, Sachna.